A special right triangle is a right triangle with some regular feature that makes calculations on the triangle easier, or for which simple formulas exist. For example, a right triangle may have angles that form simple relationships, such as 45 degrees minus 45 degrees to 90 degrees. This is called an angle-based right triangle. A side-based right triangle is one in which the lengths of the sides form ratios of whole numbers, such as 3, 4, 5, or of other special numbers such as the golden ratio. Knowing the relationships of the angles or ratios of sides of these special right triangles allows one to quickly calculate various lengths in geometric problems without resorting to more advanced methods. Angle-based special right triangles are specified by the relationships of the angles of which the triangle is composed. The angles of these triangles are such that the larger angle, which is 90 degrees or pi 2 radians, is equal to the sum of the other two angles. The side lengths are generally deduced from the basis of the unit circle or other geometric methods. This approach may be used to rapidly reproduce the values of trigonometric functions for the angles 30 degrees, 45 degrees, and 60 degrees. Special triangles are used to aid in calculating common trigonometric functions, as below. The 45 degrees minus 45 degrees to 90 degrees triangle, the 30 degrees minus 60 degrees to 90 degrees triangle, and the equilateral, equiangular triangle are the three Mobius triangles in the plane, meaning that they tessellate the plane via reflections in their sides. See triangle group. 45 degrees minus 45 degrees to 90 degrees triangle in plane geometry. Constructing the diagonal of a square results in a triangle whose three angles are in the ratio 1, 1, 2, adding up to 180 degrees or pi radians. Hence, the angles respectively measure 45 degrees, and 90 degrees. The sides in this triangle are in the ratio 1, 1, square root 2, which follows immediately from the Pythagorean theorem. Of all right triangles, the 45 degrees minus 45 degrees to 90 degrees degree triangle has the smallest ratio of the hypotenuse to the sum of the legs, namely square root 2 halves. Of all right triangles, the 45 degrees minus 45 degrees to 90 degrees degree triangle has the greatest ratio of the altitude from the hypotenuse to the sum of the legs, namely square root 2 quarters. Triangles with these angles are the only possible right triangles that are also isosceles triangles in Euclidean geometry. However, in spherical geometry and hyperbolic geometry, there are infinitely many different shapes of right isosceles triangles. 30 degrees minus 60 degrees to 90 degrees triangle. This is a triangle whose three angles are in the ratio 1, 2, 3 and respectively measure 30 degrees, 60 degrees, and 90 degrees. The sides are in the ratio 1, square root 3, 2. The proof of this fact is clear using trigonometry. The geometric proof is: draw an equilateral triangle ABC with side length 2 and with point D as the midpoint of segment BC. Draw an altitude line from A to D. Then add as a 30 degrees minus 60 degrees to 90 degrees triangle with hypotenuse of length 2, and base BD of length 1. The fact that the remaining leg AD has length square root 3 follows immediately from the Pythagorean theorem. The 30 degrees minus 60 degrees to 90 degrees triangle is the only right triangle whose angles are in an arithmetic progression. The proof of this fact is simple and follows on from the fact that if alpha plus delta, alpha plus 2 delta are the angles in the progression, then the sum of the angles 3 alpha plus 3 delta equals 180 degrees. After dividing by 3, the angle alpha plus delta must be 60 degrees. The right angle is 90 degrees, leaving the remaining angle to be 30 degrees. Side-based right triangles whose sides are of integer lengths, Pythagorean triples, possess angles that cannot all be rational numbers of degrees. They are most useful in that they may be easily remembered, and any multiple of the sides produces the same relationship. Using Euclid's formula for generating Pythagorean triples, the sides must be in the ratio m2 minus n2. 2 Minnesota. m2 plus n2, where m and n are any positive integers such that m greater than n. Common Pythagorean triples. There are several Pythagorean triples which are well known, including those with sides in the ratios. The 3, 4, 5 triangles are the only right triangles with edges in arithmetic progression. Triangles based on Pythagorean triples are Heronian, meaning they have integer area as well as integer sides. The following are all the Pythagorean triple ratios expressed in lowest form with both non-hypotenuse sides less than 256. Almost isosceles Pythagorean triples. Isosceles right-angled triangles cannot have sides with integer values, because the ratio of the hypotenuse to either other side is square root 2, but square root 2 cannot be expressed as a ratio of two integers. However, infinitely many almost isosceles right triangles do exist. These are right-angled triangles with integral sides for which the lengths of the non-hypotenuse edges differ by 1. Such almost isosceles right-angled triangles can be obtained recursively. A0 equals 1, B0 equals 2 and equals 2, Bn minus 1 plus and minus 1, Bn equals 2 and plus Bn minus 1, and is length of hypotenuse n equals 1, 2, 3. Equivalently, where x, y are the solutions to the Pell equation x2 minus 2y2 equals minus 1, with the hypotenuse y being the odd terms of the Pell numbers. Chapter 1, 2, 5, 12, 29, 70, 169, 408, 985, 2378. The smallest Pythagorean triples resulting are, alternatively, the same triangles can be derived from the square triangular numbers. Arithmetic and geometric progressions. The Kepler triangle is a right triangle whose sides are in a geometric progression. If the sides are formed from the geometric progression A, R, R2, then its common ratio R is given by R equals square root phi, where phi is the golden ratio. Its sides are therefore in the ratio 1, square root phi. Thus, the shape of the Kepler triangle is uniquely determined by the requirement that its sides be in a geometric progression. The 3, 4, 5 triangle is the unique right triangle whose sides are in an arithmetic progression. Sides of regular polygons. Let R equals 2 sin pi 10 equals minus 1 plus square root 5 halves equals 1. Phi be the side length of a regular decagon inscribed in a unit circle, where phi is the golden ratio. Let B equals 2 sin pi 6 equals 1 be the side length of a regular hexagon, and let C equals 2 sin pi 5 equals B the side length of a regular pentagon. Then A2 plus B2 equals C2, so these three lengths form the sides of a right triangle. The same triangle forms half of a golden rectangle. It may also be found within a regular icosahedron of side length C. The shortest line segment from any vertex V to the plane of its 5 neighbors has length A, and the endpoints of this line segment together with any of the neighbors of E form the vertices of a right triangle with sides A, B, and C.